Dear students, in this video lecture, let us continue the discussion we had on generative adversarial networks. Explicitly, let us see some of the improvements to the basic GAN framework, and also let us discuss few of the computer vision applications of GANs. As discussed in the previous video lecture, generative adversarial networks has two players. First one is the generator, which takes random noise or uh, the noisy samples to generate the images that are guided by the discriminator. So the generated images by the generator are considered as fake by the discriminator, and they are spurious or noisy at the beginning, so they are considered as fake. It is genuine, or it is fine to consider them as fake by the discriminator. And the real samples are provided to the discriminator. Discriminator, by looking at both of them, gives the probability of real sample as 1 and the probability of the generated sample as 0. And the discriminator adjusts itself to give that such probabilities, while the generator try to adjust itself to score higher probability at the discriminator, and hence they confuse the discriminator. And finally, the generator images looks alike like real samples, and discriminator is unable to convey whether it is real sample or fake sample. Then the convergence is said to be happening. And this was the basic framework, and this has been applied initially for generating, say, from uniform distribution to Gaussian distribution, for example, of random variables. And then it is also subsequently applied on some of the real applications, like from generating some noisy signal sample to images of faces, or images of natural scenes and different face styles, etc. This we have discussed in the previous video lecture. We also have seen the cost function. I would like to acknowledge that the slides in this video lecture are from Professor Fifi Lee team. CS231N video lecture slides. As you can see in this slide, there are two objectives that the GAN framework has to optimize. One is with respect to the discriminator. Discriminator network, as discussed before, it tries to maximize the probability of real sample, bringing this close to 1, and tries to minimize the probability of fake sample, that is g of z, generated sample, and tries to bring it close to 0. While the generator tries to catch up itself with the discriminator and tries to maximize the probability that the generated sample by it has the high probability when passed through discriminator in finding its probability. And it can be posed as minimax cost function when we consider them together. But as discussed in the previous video lecture, the convergence of GAN or generative adversarial networks is not so simple as the conventional convolution neural networks. And since there are two objectives and both are competing each other, the convergence is little unstable. And there are several practical tricks and modifications to the cost function people proposed for improving the convergence, as well as to tackle few other aspects of the generative models, or generating more better samples. One very simple trick is both are posed as maximization instead of posing as minimize problem. This is a slight variant of GAN. This is referred to as conditional GAN. As we before this the discussion of conditional GAN, one should probably be clear on the DC GAN, that is deep convolution generative adversarial network, where each generator and discriminator both are deep convolution networks. So This is conditional GAN. Either DC GAN or the GAN can generate samples of the training data of looks, which looks quite similar to the training data. But the limitation of either DC GAN or the conventional GAN is the sample, which sample gets generated by the generator is not known a priori. So if we in the training samples, if we have, say for example, the discriminator is provided with character digits, say 0 to 9, generator may generate 9 or 3 or 4 randomly, so that we don't have control on. But here in conditional GAN, we can generate only specific class of samples that we wish to, say only 3s if you want to generate, we can generate, or only 5s or whatever. This is enforced, or this is made feasible by providing the conditional probabilities rather than providing the direct samples, so or the random samples. So here, as you can see, what this conditional GAN is cost function is, it maximizes the joint probability of d given x given y. So y is the label. So for example, if I say initially that I would like to generate 3s, then I consider say the label giving 3 here, label of 3 third class, so that is 4 probably, and then I can give the noise vector, and the here also for the discriminator I give the label 3 of 3 and then the sample 3, and hence what it is maximizing, the discriminator is maximizing is d of x given y, given that it is from class 4 or 3 corresponding to 3, we are trying to generate that sample of class 4 or y equal to 3. Similarly, this noise here everywhere we consider it as a conditional density. The label is also given to the generator as well as the discriminator, and hence in testing, so if we give the label as 3 here, whatever the noise vector we give, that noise vector through generator, the generated output will be the sample corresponding to 3 here. And similar is the case with any other data, so we can generate only shirts, only fans, etc. by conditional GAN, but not by the info-GAN, sorry, but not by the simple GAN. The another variant of GAN is info-GAN. What this info-GAN does is it goes even one step ahead. Instead of giving explicit label like a deterministic label like y equal to 3, or the class label being 4, or even whatnot encoding of the label, we give here a code vector for different classes. So for example, if I have 10 classes, say code vector for first class may be n01, code vector for second class say is a sample from n01, code vector for second class may be a sample from n11, and code vector for 8th class may be n91, so like that. So a sample from n9 comma 1, so we give a random sample with different distribution pertaining to each class. What it enforces is statistically, what over time when we give, say for example, several samples of class 3, we are giving n41 here, sample from n41 4 comma 1, and say mean 4 and variance 1. When we give such sample, so it learns the discriminator is made to estimate the corresponding mean and variance of the samples that we give here. So when we give several samples of class 3, what will be effectively happening is the discriminator generator pair is learning effectively the distribution of the code vectors as well. So due to that reason, the discriminator will be able to predict the mean of that is 4 for any class sample 3. And these when we want to generate also, when we give the corresponding code vector that is 4, we will only generate samples 3, handwritten samples of 3 here. So in a sense it is enforcing, like in conditional GAN, to generate only particular class of samples. Also it enforces this enables the tie of the distribution of code vector and learning the distribution of code vector together with the sample that we want to generate. So it's in some sense the information in code vector and the generated sample, that is z of z comma c, both are have good correlation, or we are maximizing the correlation or mutual information between the code vector and the generated sample, along with the GAN loss that we have in conventional GANs. So here, as we are minimizing over G, it is maximization of mutual information with negative sign when we consider with negative sign here. So where in mutual information can be explicitly written in form of entropy, and the explicit things are here. So the entropy of C given G means that it is the expansion involves log of P C given X, that is the actual probability of code vector given X, but we don't have the actual probability, but the estimate here we have is Q, and hence finally Info-GAN framework has a cost function which is calculating the mutual information between the estimated distribution here and the code distribution that we give, and maximizes that. You can see the more explicit discussion on the cost functions in the respective paper by Chen et al. The advantage of this info-GAN is, say for example, not necessarily that we want to only generate samples of third class, fourth class, and like that. Now all rotations can be tied to a particular distribution now. So for example, if I want to generate rotated samples, my objective is to generate chairs but with different rotations. I can give some code vector pertaining to rotation, and I want to generate with different scaling. I may give different code vector that is in essence tying the scaling. So another code vector to generate chairs from tables, etc., like that. So it has much more flexibility in generating different varied samples in info-GAN, and this is also known that it entangles the features. That means, say for example, all eyes, nose, for example, if we consider as different features for face, learning face, it somehow or disentangles the information of this to that, and it enables to generate say in some sense either to enforce uniqueness or to enforce diversity in that feature alone. Okay, so let us see now some of the applications of this generative adversarial networks in computer vision. So before we start discussing on object detection and few other applications, let us see some simple application of GAN. So that is super resolution. Usually for doing super resolution, there have been several conventional methods, and there are some deep learning methods as well. The deep learning methods are convolution networks methods takes original image in low resolution, and through set of pooling, convolution and pooling, you will get the feature extraction, and after that unpooling and upsampling and layers and convolutions, we get a high resolution image at the end. The dimensions are figured out for the kernels, etc., in such a way that the strides and dimensions are figured out in such a way that the super resolution can be achieved either by 2 or by 4 or whatever with respect to the original image dimensions. So if it is original image 128 by 128, then we can accomplish up to 256 by 256 if it is upsampled by 2, and if the architecture is modified to come up with 4x, that is 4 times the super resolution, then we will get 512 by 512 here. And the cost function usually used in this kind of super resolution through deep learning is mean square error based cost function. That is the error between the high resolution image, original image, and the generated image has to be like, or the output image has to be small, and the super resolved image has to be as close as to the original image, and even the features of the high resolution image and features of the super resolved image are to be close. So when we consider now GANs framework, what we do is assume that we generate some super resolved images here, and we would like to verify this super resolved image. We do not directly give a mean square error here for considering adversarial loss. We give the output super resolved image here, real super resolved image or high resolution image. So the loss comes from here to adjust the discriminator, and the super resolved image is given as input to the discriminator. So given this super resolved image as input to the discriminator, and this discriminator networks maps onto the saying whether it is 1 or 0, comparing the super resolved super resolved image that it gets from generator and the actual high resolution image from the data set. So the discriminator essentially compares the super resolved image from the generator and the true super high resolution image from the data set. Please note that now this whole framework, that is the deep learning framework, acts as the generator. Okay, and the discriminator try to check the closeness between the super generated image, super resolved image, and the ground truth image. And now as you can see, this is the total cos function, where the previous two cos, say so L mean square error is LSR, is roughly same as the content loss or the mean square error loss. It is roughly same as the conventional methods, but there is a new loss function that is added, that is adversarial loss. This adversarial loss is shown to improve the performance for better super resolution. And you can see usually we have actually mean square error, direct mean square error, and content loss is written here. That is features of the high resolution image compared with features of the ground truth or generated image. Features of the generated image are compared with features of the image in the data set, high resolution in the image in the data set. And you have an additional GAN loss here. Okay, this is the paper where you can see the more details on it. Similarly, the GANs frameworks have also shown very good success in object detection. What people have done in object detection is, especially small objects detection is a very important problem and difficult problem. The conventional frameworks like YOLO or fast RCNN etc. cannot detect the objects which are of very small scale. As you can see here, the objects are very minute scale. Usually the objects having less than 30 cross 30 pixels are referred to as small objects. So in such case, what we can do is, for example, if fast RCNN or the mask RCNN gives several object proposals, that means several proposals. Among these proposals, there may be some cases where the conventional fast RCNN training will not be able to detect them as objects with high probability. In such case, we apply a generator as a super resolved network, like exactly what we have done before, and this whole thing becomes the generator now. So along with the baseline detector having the region proposal network and followed by the generator network that is super resolving, the super resolution of the small proposals is what is the generator now. And once the super resolve the proposals are super resolved, these super resolved proposals are compared with the proposals of that class or different classes, and that mm, uh, and discriminated. In fact, it is proposed to the proper ground truth class, corresponding class, and the discriminator takes a call whether it is same class or not, and also it will say whether the discriminator is also says enforces on the bounding box regression. So it adjusts the proposal XYSW, and also it enables us to decide the class label, and also finds a adversarial loss, like saying that whether the generated image is fake or true. So now this discriminator network is having the conventional object detection losses like fast RCNN losses, classification and regression losses, plus the adversarial loss, while intermediately the generator network here is super resolution. So what it is essentially doing is, the object generating object proposal to super resolution is considered as generation of the high resolution objects of the small objects, object samples of the small objects, and discriminator verifies their location, the class label, and the whether they are how close to the real samples. And this whole thing is trained in both adversarial loss plus the content loss or the unbounding box regression, and this gives reasonably good accuracies compared to the conventional YOLO or RCN for small object detection. Similarly, there is another framework proposed roughly the same time, that is on perceptual, using perceptual loss. The idea here is, rather than comparing the objects in super resolution super resolved objects, can we compare the super resolved features for better detection of the small objects? So now the framework has a generator that do super resolution of features here. Previously the frame generator was super resolving the object, small object proposals, and this now super resolves features, and there is no like there is no object detection essential. Here we will see the explicit details in the next slide. Small objects are those which are lesser than 32 cross 32 pixels, and medium objects are between 32 pixels, 32 square pixels to 96 square pixels, and large objects are above 96 square pixels. Since small object detection is of important problem, especially in signboards and few other important classes, so there is a data set that explicitly deals with the small object detection. And this is the framework where of once the generator, the object of generator is very clearly shown here, that is to superize all the features. This is the whole framework where you can see the discriminator has two losses. One is adversarial loss and another is the perceptual loss. This is exactly similar to having fast RCN kind of loss, where you have classification loss plus the regression loss. Here, as you can see, the small object, assume that there are bigger objects in the data set as well as smaller objects. We have assumed that we have features from the bigger objects already stored in the database. Now what we are trying to do is, so when we have smaller objects detected by say for example conventional methods, these objects features are sent, and these like coarse features are added with the super resolved fine features, and the total as total sum gives us the super resolved finer features of the small objects. These super resolved features are compared with the ground truth object like bigger size object features or resolved features, and then large object features, and then the discriminator takes a call whether the generated features here are fake or real. In addition to that, we also enforce the classification and regression losses exactly like in fast RCN. But however, here at the discriminator. Please also note that the here the fs discriminator, what the generated sample is fs plus small features of small object plus the features of the small object through super resolved features of the small object. Okay, that is super resolved features. Okay, so let us see now another framework for say, let us see another application for GANs. This is on visual tracking. So where there are some sophisticated methods for visual tracking through GANs, one or two methods like Whittle and a few other recent methods. Here it's a simple extension of GANs for visual object tracking, referred to as adversarial learning for visual tracking also. Here what we are doing is assume that this is by our group. So what the students are doing here is, so we have actually a target image and a search region, and we want to find out where this object is in the search region, for example in a given frame. Now features of the target are length and features of the search region are also length. Since the search region is bigger size, we have the high like 22 cross 22 features here, for while the target has 6 crosses. The correlation between these two gives the response map, and higher the value of response map, it indicates that that is the probable location for the object. And this probable location may not be very exactly matching with the target location. So now the discriminator is here to adjust this misalignment with respect to the target location. And to do that, what we are doing here is, say for example, once the target location patch is considered, the these like generated patch, that is predicted patch from the generator, or the generated patch is compared with respect to the real patch, and the adversarial loss is back propagated. Simultaneously, the mean square error loss between the predicted location and actual location are back propagated here. So like exactly we have the mean square error loss directly back propagated to the generator, and the discriminator also enforces the learning through adversarial loss. And as you can see, this gives reasonably some boost with compared to the existing frameworks. It is also seen that the adding of mean square error loss in addition to adversarial loss is useful. So this is another application, one of the well-known application referred to as cyclic GAN. So what the objective here is image translation. Usually if I want to translate some background of the image or the image itself, it is not very trivial. Usually people do it pair by pair. That means, for example, if I have some set of sketches and if I have some set of colored images, this sketch can be paired to the corresponding color image, and then each of the sketches paired to the corresponding color image, and then they are learnt in pairs. But that pairwise learning will only make the corresponding pairs to learn together, and it doesn't enforce the generality, or it doesn't give high general learning for the network. Here the cyclic GAN is one of the celebrated method, where you can generate from one class of images as a whole to another class of images without pairing before. That means this background and this horse need not be paired to only this zebra and this background. So these both can be completely different. So for example, while training, I can take any random sample from class A and any random sample from class B, and still I can train that overall to get the general mapping between horses to zebra class or zebra to horse class. That is one advantage. Second thing is the cyclic GAN, as the name indicates, it enables us, it has two generators and two discriminators. Thus, simultaneously, it learns translating from zebra to horse and horse to zebra. Okay, well, how is it done? So, assume that, so there are two depictions of the cyclic GAN, where in one of them we are trying to learn translation from horse to zebra. In this, we are trying to translate from zebra to horse. So both in fact use same generators, same set of generators and discriminators. Please make sure that um, while translating from, for example, transforming from zebra to horse, this is the main generator that it is generating now. What it is generating? So it is generating here, for example, if I start from this input zebra image, it generates to it learns to map generate the horses here. Once the horse is generated, it is this it is compared with respect to the ground truth horse or the real horse, to check whether this is like the discriminator gives fake, whether this is fake or real. And then this, through generator A to B, generates the zebra here again. Now this discriminator B checks this generated zebra with respect to the ground truth zebra which we have, and says whether it is fake or real. So, and hence this discriminator gives feedback to this, and in this discriminator gives feedback to this. Okay, and these are adversely lent and these are adversely lent. And now uh, while learning to translate while learning to translate horse to zebra, now this becomes the input, and this is this generator A to B learns to translate translate to zebra. Once it learns, then this discriminator compares with the respect to the ground truth zebra, and says whether it is zebra or not, fake. And similarly, this B to A generator will generate generate the horse, and these two are compared, since it is ground truth and this one compared, to say whether this is horse or like fake, generated one is fake or true. And this way of ensuring generating from horse to zebra and zebra to horse goes side by side together, and in effect the generator, if I use only generator A to B later, then I will be able to generate the horse to zebra, and B to A if I use, I will be able to generate zebra to horse once the training is over. Thank you.